Okay, so this is going to look at EMF and internal resistance. EMF is known as the electromotive force, or the idea of what a battery is providing to cause electrons to move throughout a circuit. Right? So if we take a normal circuit, here is our load resistance, right? And then there is some voltage provided by the battery, right? So this here is going to be my EMF, right? Just another fancy word to say voltage, right? But it's typically only used when we deal with internal resistance, okay? Which this is my internal resistance here. If you think about it in terms of the battery itself, if this is the battery, right? Here's the positive terminal of the battery. Here's the negative terminal of the battery, right? The battery itself has an EMF, or electromotive force, okay? However, when we would to it, that voltmeter wouldn't read what the EMF reads. This would be the voltage of the circuit, right? So those are going to be different. Typically, you're going to deal with them as the same, but when we're dealing with internal resistance, the voltage of the circuit is going to be a little bit different than the EMF of the battery. And so the basic equation is the EMF is equal to basically the voltage of the circuit plus the voltage that is lost in the battery, right? And so that's this internal resistance, which is the voltage loss, right? If we think about it, that's going to be the current times the resistance of the load, the resistance of the circuit itself, plus the current, because this is a series circuit, times the internal resistance, which is typically labeled as lowercase r. Right? Based on that, we can say that is capital R plus lowercase r times the current is equal to my EMF. Right? So let's go through just a few examples of this and kind of put some numbers to this to see how this would work, okay? So if we think about a circuit that has a load set up of 100 ohms, has an internal resistance of 2 ohms, right? And then what we're able to do is we're able to know that the battery itself should have an EMF of 12 volts, right? And what we might want to know is kind of what's the current of this circuit, right? As well as then understand what is the voltage of the circuit, right? And what is the voltage lost, right? Due to that internal resistance, okay? So I'm going to use this equation. The EMF is equal to IR plus IR. So that's 12 equals I times 100 plus I times 2, right? And if we were to calculate that then, that would give me 12 equals 100 into I, which would give me a current equal to 0.118 amps. And I'm going to go out to 3 sig figs here just because the rounding actually doesn't help in terms of, because this voltage here, or this resistance here, is so much smaller, right? The rounding kind of, if we were to round this to 0.12, it really doesn't work out very well. So keeping that third sig fig actually helps us see what's going to be happening here, right? If I were then to use that current back into my equation, right, I can find that this value here, I times R, is 11.8. And I can find that this value here is 0.2 volts, right? So the voltage of the circuit is equal to 11.8 volts. and that means the voltage loss is equal to 0.2 volts. So if I were to have a voltmeter hooked up on either side of my battery, it would only read 11.8 volts because some of that voltage is lost within the battery, right? That 0.2 volts is lost here, whereas then the rest of the circuit can only use 11.8 volts, okay? So that's what it's going to look at like when I'm dealing with an internal resistance. While typically without internal resistance, we would say that this resistor here would accept 12 volts. It's actually only going to be 11.8 because we have some energy or voltage lost due to that internal resistance. Another example we can look at is a very similar setup, but this time in parallel, right? So it may be a little bit more complicated type of setup. Okay, so this is going to be a 50 ohm resistor. This will be a 100 ohm resistor. This here will be a 5 ohm resistor, and then we'll have an EMF of 12 volts again here, right? So here's my battery, okay? And trying to understand kind of what voltage is occurring in all of these scenarios. So I'm going to simplify this circuit now by doing my parallel resistors. I'm going to find that this resistor here is 33.33 ohms. I still have my internal resistance of 5 ohms there. This is 12. Okay. And now, because it's just a simple circuit, I can use my equation I R plus R. Okay, so this is here, this is my load, my total load of the circuit here, my internal resistance. From that, I can find my total current, and then I can solve for my EMF, or I can solve for, in this case, I can solve for my current, and kind of use that in going backwards, right? So if I were to do that, in this case, this is going to be 12 volts equals I times, this is going to be 38.33. So my current in this circuit now is going to be 0.313 amps. Okay. As that goes through, as that current is moving throughout this circuit, then I can solve for the voltages at each location. The voltage across this resistor then is going to be 10.4 volts, and the voltage across my internal resistance is going to be 1.57 volts, right? So what we see is while the voltage of the battery is 12, right, it's actually only going to provide 10.4 volts. And this is because my total resistance is actually somewhat close, right? It's only about 6 times greater than my internal resistance. So this is going to take about 1/6, just a little bit less than 1/6 of my total voltage, right? So from that, I can find this. And what this tells me then, this again is my voltage lost due to the internal resistance. And then this here is 10.4. This is my voltage of the circuit, right? So going back here, I know this is going to have 10.4 volts. This resistor here would have 10.4 volts, right? And so I can use that to understand how the EMF at 12 volts is actually only going to be able to distribute 10.4 volts throughout the circuit because of that 1.57 that's lost in there.